Hi guys, this is a quick video to get you a little more up to speed with the idea of weighted averages so that you too can calculate an atomic weight from a bunch of isotope data or dig out the natural abundances of a few isotopes based on knowing the atomic weight and those isotope masses. To do this, we need to look a little bit at this concept of a weighted average, how it is that we calculate something where a bunch of the atoms in this case have one mass, a whole bunch of others have another mass, and we want to know the average mass of any individual atom. This comes in very handy for us when we're dealing with big samples because we don't really care about each individual isotope in that case. We care about all of them all at once, ostensibly at their natural abundances. And so just to kind of give you an idea of how this works, if I were to give you guys a test, and let's say I had 5 students take the test, 4 of them got a 100, 1 person got an 80. I think you can see, I hope from this, that the average score on that test wouldn't be a 90, even though it's smack in the middle of these two, because that's not a fair representation of how the class on the whole did. Many more people got hundreds than got 80s. And so in that case, the way we deal with this is to average this way, essentially 100 plus 100 plus 100 plus 100 plus 80. So each one gets represented properly, and then we divide it by the total number. That would give us the average here, which is going to come out to 480 over 5, which would be 96. But take note of the way that I did this. Essentially, this is just 4 times 100 plus 1 times 80 over 5. And so if I have information about each of the individual things, or if at the very least I know how they compare to each other, how many scores were this, how many scores were that, I can go ahead and calculate a weighted average this way and come up with something that's more representative of it. In this case, the average score is a 96 because hardly anybody lost points. Now, looking at the atomic mass example, the information we need is not just the isotope masses or the identities of the isotopes. We need to know exactly what percentage of the atoms are each one of these. So in the case of carbon, the vast majority of it, 98.9% of it, is this isotope, carbon-12, 6 protons, 6 neutrons, 6 electrons. This is, by the way, you'll notice it's got an exact number here, 12, as its mass. This isotope is the basis for the definition of what an AMU is. An AMU is defined as 1/12 the mass of this. So that ends up being an exact number for us. The next one down, not quite an exact number, although you'll notice that the atomic masses for each isotope are pretty close to the mass numbers in general, because a proton at rest has a mass just a little more than 1 AMU, so does a neutron. So when I add them up, essentially I get roughly that many AMUs, but it is a little bit off to one side or the other. Now we can see just from subtraction here that 1.1%, roughly 1 out of every 100 atoms of carbon, are this isotope. And it may not make a huge difference to its chemical properties because those largely depend on the electrons, and the number of those depend entirely on the protons. However, it does come up in certain types of spectroscopy. You can actually see the amount of each that you have. You can see the effects in terms of vibrational frequencies from having something a little heavier on one side of a bond, so it doesn't vibrate quite the same way. The other thing that comes up here with carbon-13 is it's got different magnetic properties that give birth to an entire type of spectroscopy called nuclear magnetic resonance. It's the same thing that we use for magnetic resonance imaging. You'll definitely see carbon-13 show up in organic chem because it's part of how we figure out the structures of organic compounds. So in order to find a weighted average, now that I'm done with that tangent, all we're going to do is the same basic thing here. Notice that in this case the natural abundance of 100s was 4, and the natural abundance of 80s was 1. Here what I'm going to do is take the 98.9%, and I'm actually going to look at it as 98.9 out of 100, being 12 AMUs. And then from there, I'll go ahead and examine carbon-13 being 1.1 out of 100. And that's now 13.0033 AMUs. And so notice that in this case, rather than deal with the denominator here, I'm just going to represent the percent as a fraction. And when I do that, if I add these guys together, it should give me an average mass for this particular substance. And you can plug that into your calculator, but what you'll find is it's a number that you've seen before. It is the atomic weight. Now let's take a look at how we would deal with this if we knew this stuff and that, but didn't know those. Okay, we've got some bromine data up here on the board, and like chlorine, which you dealt with in one of the homework problems, it's got two isotopes that largely make up the bulk of its mass. The other isotopes of bromine aren't very stable, they don't persist for very long, and so their natural abundance is practically zero. Now, these two isotopes have a pair of masses that are near 79 and 81, but if you look at the periodic table, you'll find that bromine has a mass of just about 80 AMUs for its atomic weight. So the weighted average is 79.906 AMUs. And so we're going to work this one in reverse. We know the answer at the end. What we don't know are those natural abundances. How different are those mass spec peaks that you've been reading about in TRO for this particular element? And if we want to figure this out, we're going to try to appeal to what we did down here. And I'm going to just kind of tip this to you guys right now. One of the easiest ways for me to try to create an A problem on a test is to take a process that you have been doing in one order, heading towards one answer at the very end, give you the answer and take away something in the middle. And so that's essentially what we're going to do here. Because if I look at the expression that we had for carbon a little while ago, what I'll notice is that now I don't know those numbers. I know these, and I know the final answer. I know the atomic weight, but I don't know those two natural abundances, and that's what I'm looking for. Now there's a small problem we're going to run into. If I try to fill this in by analogy, I'll say that x over 100 times 78.9183 AMUs plus y over 100 times 80.9163 AMUs is equal to, well, that. We'll just bring that down. If you're a little bit experienced with algebra, you'll recognize there's a real problem here, which is that it's one equation, but two unknowns. So technically I can't solve this unless I can come up with another relationship between x and y. Lucky for us, we have one of those, because I just told you that these are the only two isotopes of bromine. So take a guess. I'll give you a moment of pause as to what x and y have to add up to. Okay, took your moment. I hope you said 100. And so what that's going to mean is that if I just want to look at x, I can represent y now, since x plus y equals 100, I can represent y as 100 minus x. If I subtract x from both sides, it's still a good equation. And so that's exactly what we're going to do. And so at this point, now we've got something we can solve. 100 minus x over here, x over here. Once I solve for x, which is going to be the percent abundance of the bromine, I can then go ahead and subtract that from 100 and come up with the percent abundance of bromine 81. The rest of this, I'm going to recommend you go ahead and try out on your own, because it's going to get pretty darn crowded on this board and hard to see, and really at this point it's just a matter of simplifying a few equations. The real trick in chemistry is the setup. One last quick hit for you here. I wanted to take a moment just to show you what I discussed at the very end of class about how to figure out how much excess reactant is left over after a reaction's done. Remember in class we looked at what happens if I mix 5 grams of titanium and 5 grams of chlorine, and we had determined how much of the TiCl4 product we could make from each of those if we had started with 5 grams of that and as much of the other thing as we needed. And we discovered that chlorine was going to be the limiting reactant for this reaction, so we would only make a little under 7 grams of titanium chloride before the before the chlorine itself ran out. Now, I mentioned in class that one way we could figure out the amount of titanium left over for this kind of reaction is just subtracting off the 5 grams of chlorine, because whatever other mass there is here must be the titanium. But if we have a reaction that has more than one product, that's not going to work for us. And there is a foolproof method that will always get you the right answer here. So this is the way to do it. In this case, we can use the stoichiometry that we know to go from the amount of chlorine that we consumed, which is the full 5 grams, over to just simply the amount of titanium that is going to be reacted. To do that, we do the same old thing. 1 mole of chlorine equal to 70.906 grams of Cl2. And then we're going to need a mole ratio. We need to get to the amount of titanium. So in this case here, we use the chemical equation, 1 mole of titanium for every 2 moles of Cl2. Lastly, we convert over to the mass by making use of titanium's molar mass, 47.87 grams of titanium in 1 mole of titanium. And so with these steps, grams of chlorine cancel, moles of chlorine cancel, moles of titanium cancel, and I don't even need a calculator. I know what the answer is. We figured it out earlier. But verify this for yourself that it still results in the proper response. That's how much titanium was used. And so the amount left over is still going to be 5 grams of titanium minus 1.69 grams used to give us 3.31 grams excess titanium. That will work regardless of what kind of reaction you've got, so take it to the bank.